So before we talk about bandits, let's talk about combinatorial. So here, if everything is known in the problem, you have a combinatorial optimization problem. So of the most general sort, you have a discrete set that I call calligraphic M, and it's a set of vectors of dimension d that with components either 1 or 0. And you have a bunch of weights, which is a vector in 0, 1 to the power d. And what you're interested in is simply to maximize the dot product between M and theta when M is in calligraphic M. So a well-known example of this is the maximum weighted matching problem. So you have the complete bipartite graph as depicted here, and you can encode each perfect matching as a vector with either 0 or 1. So a perfect matching means that each item on the right gets assigned to each item on the left gets assigned to exactly one item on the right. Okay. And we know how to solve these things like Hungarian algorithm or whatever. So now how do you make a bandit out of this? Just take deterministic stuff and replace it by random variables. So same problem, except that before you had a weight assigned to each edge, which was called theta ij. Here I replace it by a random variable called xij with the same expectation, and I'm going to try to learn, let's say, the maximum weighted matching in an online manner. So I'm going to try some matchings, look at the realization of the cost, and iteratively try to maximize that. Okay, so the important detail here in that problem is the feedback. So you have two types of feedback. First, so basically how does it go? So you have rounds indexed by n, it's discrete. And at n, you choose m of n, which is the decision at time n, and you choose it based, of course, on past observations. You're adaptive in some sense. Then there's a vector xn that you don't know. And what you observe, you have two cases. So the first case is the most brutal one, is the bandit case. You simply observe the dot product between m and xn. So you only observe the cost, if you will. You don't observe any individual element of x. And the second case is called the semi-bandit. So semi-bandit means that if you have select each time there's a 1 in M, I reveal you the corresponding component of X. So in a sense, you can think of M as choosing a set of components from X. I reveal you this. So you can, of course, calculate the dot product between the two. So there's more information here than here. Okay? So now, standard stuff. Here you're trying to minimize regret. So the regret is simply the difference between what an oracle would obtain. So an oracle is a guy who would have known all the extents in advance and would have chosen the best static decision. And then you have your algorithm, which is the cumulated dot products between Mn and Xn. Okay? And once again, you have two typical assumptions here, as in all bandit problems. You have either the stochastic assumption. So stochastic assumption means that Xn's are IID. They are with expectation theta. Theta is the latent parameter we're trying to learn. And so here, just something to be noticed. We assume that the components of X are independent. So that's not what is generally assumed. And I'll tell you why I assume that and why it actually does make sense from a sort of engineer point of view. Although apparently engineers can't understand bandits, but I'm convinced of the contrary. Anyway, and so adversarial, well, you said it. At the beginning of the experiment, you have an adversary who writes all the xn's, x1, x2, etc. in an envelope. It gives you that envelope and you play against the envelope. So it's not a game theoretic adversary. He cannot change xn's as a function of your action, but it's the worst case assumption, if you will. Okay, so once again, a tiny bit of engineering. So why do we do that in practice? Why do we do that? Except for doing a bit of cute mathematics, this problem actually makes a lot of sense in practice if you're a network engineer. Because all you do as a network engineer is combinatorial bandits. So there are two typical examples. More or less. You do combinatorial bandits without knowing them. It's like Monsieur Journal. Anyway, so the first thing that you do if you have a communication network, you want to do routing. So you have two nodes, the source and the destination. In between, you have a bunch of paths. So here I've made three paths: the blue path, the red path, and the black path here. And to each edge, you associate a cost, which is usually the delay. And you want to find the path that minimizes the sums of delays. So that's a combinatorial bandit, of course. Here, the set you're optimizing over is the set of paths. and D, the dimension, is the maximal length of a path. And usually, I mean, if you've done a bit of like network engineering or queuing theory, it makes sense to assume that the delays on each path are independent. So you can think of Jackson networks or Kelly networks, whatever. And it's important to understand that when you assume independence, the problem gets easier. And I'll quantify that later on. So you're using a more structure than if you didn't assume that. Okay? And second thing that wireless engineers do, they assign channels to users. So you have, once again, maximum weighted matching problem. And here, the elements on the right are, on the left are the users, and the elements on the right are channels, like think of wireless channels. So here, once again, if users are far enough, and here, of course, the reward of each edge is the data rate. You're trying to maximize the total amount of bits that can be transmitted in an amount of time. So here, once again, you have independence across all those things due to two things. Due to the fact that the variability in data rate is due to fading, so it's the wireless medium, the random scattering. And if users are far away from each other, then you have this independence. And yeah, that's it. Okay, so now I'll focus, for this presentation, I'll focus on one case out of the four. The case is stochastic and semi-bandit, so you have four combinations. And there is also bandit adversarial in the paper. You can check it out here. I'll try to keep it short and sweet. So how do we calculate the difficulty of the problem? So you have three parameters. First one is the dimension, the number of items. I call this D. Then you have the decision size. The decision size is the maximum number. If you take any decision, the maximum number of components that can be equal to 1. And you have the optimality gap, so if you're a bandit guy, you know that when this thing grows small, the problem grows difficult. Because you have to distinguish between two random variables that are separated in expectation by delta. So here, this is some statistics I collected. So this is like one paper, the regret, etc. This is us, this is the beginning. And you can notice steady decrease in terms of regret, so roughly like it's being divided by m each year. And so the point is that there are some things that are avoidable and some things that are not avoidable. So the factor D here is not avoidable. You can prove that. The factor log T is not avoidable. That's like Lyle Robbins plus. The 1 over delta mean is not avoidable. What is avoidable is this polynomial in m here. So you have m3, m2, m. And here you get square root of m. So I'm under the belief that this is necessary, but I don't know how to prove that. So anyway.
In terms of the min-max rate, does this give the min-max rate?
No, of course not. That's stochastic, problem dependent, like a la Lyle Robbins.
No, but what I meant is, out of this bound, you can get a distribution independent bound.
Yeah, of course, yeah.
And the one you get is minimax optimum?
I wouldn't think so. Because when I'm talking about lower bounds, I'm talking about Lyle Robbins style.
Of course, I understand that if when you get, when you derive a distribution independent bound from this, you don't get the minimax, then...
No, because you have some additional terms that depend on delta min, of course. Yes. That's not what we're trying to do here. But yeah. Anyway, so if everyone knows bandits, I'm sure that's no novelty. So what you want to do is just, in general, when you solve a bandit problem, 99% of the time you come up with what you call an optimistic algorithm. Optimistic algorithm is just means this. So you plot decisions here. This is the empirical mean for each decision. So the dot product between the decision and theta hat, the estimated theta. And then you build confidence. You build confidence intervals over them. You look, so those red things here. You look at the top of the confidence interval. You call this BM of n, or you call this an index, and you select the decision maximizing that index. So first, it makes sense in terms of statistics, and actually the main reason why you do that is because there's an easy way to analyze such algorithms. And the idea is to say, okay, if I select the, yeah, that's true. You know, there are things that work better in practice, but we don't know how to handle them with equations or with theorems and whatnot. So the point is that you look at the decision M and you say, well, if M is selected, two things can happen. Either the index of the optimal decision was smaller than the optimal value, but that happens very seldom because it's indeed an upper confidence bound. And otherwise, that means that the index of your decision was larger than the optimal value of the problem. And then you can work with that term, and that's where you end up with the log t factor. Good? Okay, so now, now, if you believe me, the only thing that's left to do is find a good index, right? If I have a good index, I have a good algorithm, and I'm done. So first, this is more or less what you could do, but which is not optimal. So just calculate theta hat I of n. So this is the empirical mean of the rewards from item I. Okay. And Ti of n is the number of samples you obtain. So the naive approach, we are trying to find an upper confidence bound for something which is the dot product between m and theta being the unknown. So the simplest way to do this is just to do that component by component. Find a confidence interval for each component of theta, and then sum the confidence bonuses, and we're done. So you take out your favorite Hobding inequality. Everything is bounded by 1, let's say, or some portion, so you end up with the fact that the difference between the empirical mean and the true value of the parameter is bounded by square root of 2 times log t divided by Ti of n. So that's a confidence interval with roughly error probability 1 over t. So that's that. If you just ignore that we are doing combinatorial bandits, that's the UCB algorithm for you. Of course, in general, this is false because Ti of n is a random variable. But just pretend for now that Ti of n is fixed, does not depend on the observed samples, so on and so forth. Okay, so then that gives you the natural index, which is the empirical mean, and plus the sum over items. So mi equals 1 if the item I is in decision m, times those guys here. So that's essentially what is, I think in the literature is called the CUCB algorithm. So then, of course, your algorithm is calculate this and maximize over m, and then that's your decision. Okay, so the point is that we ignore the independence between the components of theta. So this is an index, indeed, that's larger than mu of m with high probability, but that's much too large. And the point is that we ignore the independence between the items. And once again, it doesn't take too long to see that if you look at the variance of mu hat mn, this should be roughly the sum over I of mi divided by Ti of n, the number of samples. So in a sense, we should have the same index, except that the square root here goes here. It's square root of the sum instead of sums of the square roots, right? That's, let's just pretend that I'm lying and that everything is Gaussian. That's how a confidence interval should look like. The standard deviation multiplied by something. Okay, anyway, so now let's go back to KLUCB, because we know for a fact that if you have one dimension, if you have one item, that's a way to find good tight confidence intervals. So the point is the following. So here consider lambda between 0 and 1. Calculate mu hat, which is the empirical mean, and then you draw the KL divergence between mu hat and lambda. So that gives you a curve. And then look for the region. So of course here this is equal to 0 if lambda equals to mu hat is equal to 0. And the point is that isolate here the region between B plus and B minus and B plus, such that this curve is below log of 1 over delta. So that's easy to calculate. You can do that by what we call this binary search. And then the main point of the KLUCB algorithm is that this is actually a confidence interval for theta, so that such that theta falls into that interval with high probability. And so this, if you're an information theorist, that makes a lot of sense, right? You know Sanoff's theorem. Sanoff's theorem tells you that if you draw samples, if you draw an empirical distribution and you compare it to the true distribution, the KL divergence between those two things must be small. It's going to concentrate. And so that's how you obtain the KLUCB index. The plus here is the KLUCB index. But now we need to do that in several dimensions. So once again, Sanoff. So once again, calculate theta hat of n, the empirical mean of theta, and then draw this d-dimensional potato here, which is on which the empirical KL divergence between theta hat and the parameter lambda is small. So what do I call the empirical KL divergence? It's the sum over I of Ti of n. Ti of n, I recall, is the number of samples that you obtain. And then the KL divergence between mu hat of I, the empirical mean for I, and lambda. And lambda is a vector, a d-dimensional vector, if you will. And the point is that using similar ideas, you can prove that actually with high probability, theta falls into that potato. So that's actually the main proof argument. That's the stuff that we have to prove. But if you believe me, and if theta falls into that set with high probability, then a way to upper bound the dot product between m and theta is simply to maximize the dot product between m and lambda when lambda runs all over that set. If theta is in that set, the maximum over lambda of this must be greater than m theta, right? Just definition of a maximum. Okay, so that actually gives us my index, right? So my index is as follows. So you define it as the solution of an optimization problem. So you are going to maximize the dot product between m and lambda, where lambda is a d-dimensional vector, and you're going to maximize it over that red potato that I've drawn. So this potato indeed is the region on which the empirical KL divergence is smaller than log t. I'm omitting some log t here terms for clarity, but I'd be happy to discuss log t terms afterwards. So this is an optimization problem, and if you just write down the KKT conditions, you find out that you can calculate this just by doing a line search on the corresponding Lagrange multiplier. So in a sense, calculating that guy is not more difficult than calculating the KLUCB index, which you also do that by binary search. Okay, and so if you don't like KL divergences and you're more of a Hovden guy, then you end up with this confidence interval as I predicted. So empirical mean plus the square root of the sum of those confidence bonuses. Okay. Good amount, huh? So what you can prove, I'm not going to do it here, but it's just like typical bandit stuff. You can prove that this algorithm has regret, which is d square root of m log t over delta, as I predicted. And of course, the key idea is what I told you had to believe me, is that this index, my number bm of n here, is indeed an index, so that it's greater than the dot product between m and theta with high probability. And the crucial argument comes from a previously derived concentration inequality telling you that the empirical divergence concentrates here. So this is like a multivariate version of the inequality used to prove that KLUCB actually works. And you do this, so the original one you did it by peeling, by decomposing, according to the number of samples in a geometrically increasing sequence. You can do that in multiple dimensions. It's not really more difficult, and you get what you get.
You peel the potato.
Yeah, exactly. That's what I do. Anyway, so after all the potatoes are peeled, we should try to see how far are we from the optimal algorithm. So usually, when you have trouble in life, so some people turn to God, some people turn to drinking. I usually turn to lie, and usually the answer comes. And here indeed, so the point is that there's a very general result by Lai and Graves, a PhD student of his at the time, that gives you the regret lower bound for almost any kind of bandit problem that you wish in the form of a linear program. I'll explain that linear program afterwards. And so that's already not bad. And what's even greater is that this bound is always attainable. They give an algorithm that attains this lower bound asymptotically. And it's not only a bit asymptotic, it's extremely asymptotic, if that makes sense. Very close to infinity. So, because if you implement that for t equals, I don't know, 10 to the 6 or 10 to the 7, it just doesn't work. It's too asymptotic for my taste. So anyway, who's that guy? So Standard assumption, you consider an algorithm which is uniformly good. That means that essentially it has logarithmic regret on all problem instances. So you take one problem instance, you calculate the regret, you let t go to infinity. If that grows smaller than the log, we are good. And of course, such algorithms exist. Think of any sort of UCD algorithm. And if you have this is essentially saying that your algorithm is not cheating, because if you have an algorithm, you can have algorithms that have zero regrets on some problems, but they will have linear regret on others. So it's just saying we are not competing against something that's unfair. And the point is that you're going to solve the following linear program. And what is that linear program? So you look at C, which is a real vector with positive components, and the number of components is the number of decisions. So in our case, this vector is monstrous. And what you're going to minimize is the dot product between C and the vector of the differences between, so mu star, I recall, is the optimal value, and mu of m, the value of m. And you optimize this over a convex region, which is given by this expression. So this expression is, once again, you recognize that familiar sums of KL sort of term. And what that region is telling you is simply look at decision theta and look at parameter theta and look at another parameter lambda, such that the best decision on the theta is not the same as on the lambda. So it's a confusing parameter, if you will. So in order to distinguish those two guys, it tells you that the amount of samples that we need is this. So here the meaning of CM, if you think of what CM means, if you solve that problem, you calculate CM, that tells you that decision M, if you want to obtain a minimal regret, must be sampled at least CM times log T. That's what it is. Okay? So now we are not quite happy with that, because this is an LP and I don't know how to solve this explicitly. If I knew, the problem would be finished. And second problem, in order to apply Graves and Lie algorithm, you need to solve this guy at all times. Each time at each end, you solve a problem like that, so it's infeasible. Okay, so now the idea is simply, well, let's lower bound the lower bound. So C theta, I recall C theta is the optimal regret, and there's a relatively simple idea, is as follows, is to use a covering of the suboptimal items. So how does that work? Those are my items. The red ones are the ones that are part of the optimal decision. So if I have a good algorithm, I'm going to sample them many times, I'm going to know their value exactly. Okay? So now the guys to explore are the black ones, the remaining ones. So make a bunch of decisions, I call them H1, H2, H3, etc. Such that, so those must be decisions that you're allowed to sample. And each of them contains at most one suboptimal item. And what you can show by doing a bit of manipulation on the Graves-Lie LP is that essentially the C theta will scale as the size of H, the number of those decisions, divided by delta. So if you believe me on that, you just, for each problem you can find a good set H, and for most problems, so when I mean most problems, I mean, for instance, shortest path routing, for instance, matchings, etc. The size of this guy is actually D minus M. So D minus M is a very important number. It's the number of unknowns in your problem. Because you have D things that are unknown, and you sample M of them a lot of times. So the remaining uncertainty is this, essentially. Okay, so I know you're not engineers, but I just want to show these curves to make a point. So here we simulated our algorithm and competing algorithms on the maximum weighting matching problem. So first it works, so that's us, that's the previous stuff. So yeah, I'm letting you draw your own conclusions. But I didn't do that to trash talk other people. The point is actually that here, if you calculate the Graves-Lie LP, you calculate the optimal regret. For all times we are under that curve, so we are below the lower bound. So that's not a glitch. The point is that the Graves-Lie lower bound is asymptotic. It's going to work if t equals infinity, but you can clearly build that bound because this does it. And so of course asymptotically those two things will either meet or those guys will be above this. So that draws me to formulate the conjecture, which is that the proposed algorithm is actually asymptotically optimal. And I have two, so yeah, that's essentially the last message. So I have two reasons to believe this. First of all, I believe it's the most natural extension of KLUCB to combinatorial problems. It's the same principle, same index, more or less same concentration inequalities. And what's the second reason? What did we say? Yeah, and of course, the second reason is those numerical examples. On any reasonable numerical example that you can simulate, it works better than the lower bound. So once again, if you have some hours during the holidays, I don't know, you can. That's really yeah. So yeah, I don't know if you have some free time during the holidays, maybe you can try. I don't know. I couldn't do it. And so anyway, thank you for your attention. Maybe another thing is that, so a bit of advertising. Here in the paper, we did also adversarial bandits with bandit feedback. So I believe for that problem, the state-of-the-art algorithm is called Combandit. And so here, we do not lower the regret, we achieve the same regret, but you have a much lower complexity. And the reason for doing that, the reason for this phenomenon to happen, is because that won't help you much if you don't know the problem. But if you know the problem, the idea here is that you have a distribution over the set of items, and you're trying to derive a distribution over the set of decisions, such that the marginals of that distribution are that of my initial distribution. And the point is that you can do this efficiently by using KL projections, so projection with respect to the KL divergence, like the Chisar stuff, and then using an interior point method. So for instance, in the case of matchings, you have a much lower complexity than the Combandit thing where you have to calculate the permanency. Okay, so thank you.